Once again, Adam Eldridge here, West Valley High School mathematics teacher, teaching part of the Central Cornerstone program. Today we're going to be looking at section 7.3 in the Cohen book that Central uses for their pre-calc. And today we're going to look a little bit at relating arc length and radian angle measurement, radian reference angles, finding trig function values given the quadrant the angle is in. We're going to look at a couple other identities today involving opposite angle identities. And we're also going to look at the periodicity of sine and cosine, periodic nature of sine and cosine. To start with, let's review a little bit about how we measure angles. Again, if this is my initial ray here, and we go in the clockwise direction, counterclockwise direction, then that angle measure is positive. And if we are looking at it starting with our initial ray here and we go in the clockwise direction to our terminal ray, then this is a negative angle measure. From our earlier discussion, we talked about how we could relate an angle to a radian measure with one that was given in degrees. I'll remind you of one of our conversion factors is that pi radians is the same as 180 degrees. And one of the advantages of radians, which will come into play today and especially in the lecture on graphing the sine and the cosine curve, is that with radians we don't have to worry about this degree unit. And when we start graphing the sine function, for instance, we can talk about our axes both being real number values and not having to be worrying about how do we represent a degree on a horizontal axis when we're graphing the sine function. So we're going to be looking at radians today, once again, because we're going to be transitioning into how the stuff on the coordinate axes, the unit circle, how that relates to the graph of that function. A couple other reminders that when we look at an angle, let's call that angle T, it will intersect an arc here, where that arc relationship, we talked about how if this is S and this was R, that the angle T was equal to the ratio of S over R. Now, if I'm looking at S equal to R, and more specifically, if I look at the unit circle where we have that arc length, the radius of 1, and we were to draw so here is point P, which is on that circle. Here's our unit circle, circle with radius of 1. This point right here is on that circle. This angle here is that angle T, and we can see that the x coordinate here, the x value, is equivalent to the cosine of t. Again, when we're on the unit circle, we know that cosine is this horizontal distance divided by the radius, but since we're on the unit circle here, we're looking at a radius of 1. So I know that the coordinate of this point P is the cosine of our angle. Looks like cos without parentheses. And I know that the y value is equivalent to the sine of the angle T. So I didn't leave myself much room here. But sine of T is this distance right here. So this point right here on the circle has a value of cosine of t, comma, sine t. That'll play a role when we start, again, looking at transitioning from stuff on the unit circle to the graph of the sine and cosine function. A couple other reminders. Sine is positive. The sine value is positive in quadrants where the y coordinate is positive. So sine is positive here in quadrant 1. Let me redraw. The sine function is positive in quadrant 1, and the sine is positive in quadrant 2. Sine is negative in quadrant 3, and sine is negative in quadrant 4. Cosine is positive anywhere where the x is positive. So it's positive in quadrant 1, and it's positive in quadrant 4, but negative. Oops, that looks like a theta. That's supposed to be a negative in the side of a circle. Cosine is negative here, and it's negative here. Now tangent, remember, tangent is equivalent to the sine over the cosine. Which in this case would be the y over x. Which, let's think back to our earlier math career. Anytime that I see a change in y over a change in x, my gut reaction is to think a little bit about something called slope. And as we look further at applications in trig, one of the things that comes up is the fact that tangent is related to the slope of this line. So tangent is equivalent to y over x. So anywhere that both sine and cosine are positive, the tangent is positive, or whenever sine and cosine are both negative, which happens in quadrant 3. Tangent is negative when only one of them is positive and the other one is negative, which is in quadrant 4 and in quadrant 2. So that's a little bit of review and tying in the fact that the cosine of this angle right here is equivalent to the x-coordinate on the unit circle. Similarly, the sine is equivalent to the y when we're on the unit circle. If we're going beyond the unit circle, then we have to divide by the radius. So cosine of t is equal to x over the r. So x would be equal to r times cosine t, and y would be equal to r sine of t, which when we get to polar coordinates, that'll play a role in some polar coordinate conversions down the road. So all this stuff will tie in later on to some concepts in polar coordinates, as well as some work that we'll do in calculus. So let's look at an example of how I can give you one of the trig functions values for an angle and ask you to find the other 5. So for my example, let's say that the sine of angle t is equal to 2/5. And we know that t is between pi over 2 and pi. And when we talk a little bit more later on about the periodic nature of sine, we'll look at why we need to make a restriction like this to solve this value. So I want you to find the cosine of t, the tangent of t, the cosecant, the secant, and the cotangent, all of angle t. And this is a non-calculator exercise. We can do this without a calculator. One approach, and the approach that I favor, is to always draw a picture of the situation. I know I'm dealing with an angle t that's somewhere over here. Okay? I know that I'm between pi over 2 and pi. And I also know that this angle has a direct relationship to this angle. This would be our reference angle. I'm going to create a right triangle here. And I know that the sine of this angle is equal to 2/5. That means that the side opposite compared to the hypotenuse of that right triangle must be 2/5. Which brings us to the Pythagorean theorem, because I also want to know what's this horizontal distance right here. So this horizontal distance is going to play a role in some of the other trig functions. So let's take a moment and say, okay, I've got 5 squared, that's my hypotenuse squared, is equal to 2 squared plus, I'll just call it x for now, that value of x which I don't know. So 25 is equal to 4 plus x squared. X squared is equal to 21. So x is equal to plus or minus the square root of 21. Now here's where I like to draw a picture, and again, I don't always see this notation in books quite this way. But I'm making a decision here on how I'm going to treat this value. Is it a positive or negative? Based upon location, I'm over in quadrant 2. I'm going to write that in as a negative root 21. So now I've got a triangle with all sides here, and I can go back to my basic right triangle trig to define the trig values of each of these other functions. So cosine of t is negative root 21 over 5. Tangent of t is equal to 2 divided by the opposite of root 21, which we can rewrite as negative 2 roots of 21 over 21. And then for the values that go with these, if the sine is equal to 2/5, then cosecant is 5/2. Secant is negative 5 over root 21, which is negative 5 roots of 21 over 21. And cotangent would be of t is equal to negative root 21 over 2. For me, by drawing this triangle out, it cues me to where I have negative and positive trigonometric values. The sine goes with the y coordinate. Wherever the y is positive, the sine will be positive. Cosecant is tied to the sine for the same reason. So notice that my cosecant value and my sine value were positive. All of my other values involve this x, which is negative, and so you'll notice that all of my other trig values here are in fact negative. Now I mentioned that there were a couple different approaches here, and it really is a similar approach just without the picture. And let's see if I can create some space here. I know that sine of t is equal to 2/5. And I know from previous discussion that sine squared plus cosine squared is equal to 1. So if I know the sine value, then I can calculate the cosine value. And this is going to look really similar to some of the calculations I had on the board on the previous slide, in large part because on the previous slide I used the Pythagorean theorem. Well, this is the Pythagorean trig identity, which we generated back in chapter 6 using a Pythagorean, a right triangle. So a lot of these calculations are going to look very similar, and it's not just coincidence. It's because they're both directly tied to the Pythagorean theorem. So 2/5 squared plus cosine squared of t is equal to 1. So cosine squared of t is equal to 1 minus 4/25. 2/5 and 2/5 is 4/25. So cosine squared of t is equal to 21/25. That's what cosine squared is. So cosine of t is equal to plus or minus root 21 over 5. Again, based upon location, the fact that the original problem said that our t was between pi over 2 and pi, we know that the cosine is negative in quadrant 2. So cosine of t is negative root 21 over 5. From this, we can take sine divided by cosine and end up with the tangent. And similarly, we can find secant, cosecant, and cotangent. So one of our big objectives today was, given one trig relationship, can you find the other corresponding trig values? Next identity we want to look at takes us back to Math 153 when we talked about odd versus even functions. And this will also lead into the graphs of sine and cosine, which we'll be doing down the road here shortly. And let's remember something about odd functions. First of all, an odd function, if we take the opposite x value, it maps to the opposite y, the opposite output, in this case an f of x. So an example of a function that is odd would be like a cubic, y equals x cubed, which if I look at the value of x, this is x comma f of x, there's some symmetry around the origin here, rotational symmetry around the origin, and if I go to negative x, the opposite x, my coordinate would be opposite of x, opposite f of x. That's the behavior of an odd function. There are some symmetries. It's got rotational symmetry around the origin, for instance. If I'm looking at an even function, one of the even functions we like to look at is y equals x squared, or f of x, I should say. And here, I'll have a coordinate x, f of x, and if I put in the opposite of x, Ben's not responding there, opposite x, I get the same output as when I put in the original x. So with even functions, if we change the input to the opposite, we get the same output as the original. Well, you'll notice down here that sine is an odd function, as is tangent, and cosine is an even function, for values of which we're defined. And we'll look a little bit more at the tangent one. It's got a different style of graph here than the sine and cosine. We have some domain issues to worry about, and you'll look at that more down the road. But let's look at another reason why this is the way that it is. If I take this angle, let's call it t, and I take this angle, which is the opposite of t, and let me grab a highlighter value here, switch my color. This value right here is going to relate to the sine of angle t. That's going to be the same absolute value, the same distance as this value. They just have opposite signs. So we're getting opposite values when we go with the opposite angle. But with cosine we're dealing with this distance here, which if we're looking at angle t or the opposite of angle t, in either case, we end up with the same x associated with it. Which is why we see that even if I go with the cosine of the opposite value of t, I still end up with cosine of t. Finally, when we go back to the unit circle, or any circle for that matter, and we chart an angle along this path. So here is angle t. If I start here at the positive x-axis and work through a full revolution and then come back to that same terminal ray, the triangle that I would construct there would be the same in either one of those cases. Like let's say that angle t was pi over 4. And I wanted to look at where is 9 pi over 4. Well, as I trace here, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 9 pi over 4, I end up with the same triangle once again. So when I look at the sine of pi over 4, that's going to be the same as the sine of 9 pi over 4. It deals with the fact that sine is a periodic function, meaning it repeats the same pattern over time. There are many examples in the real world of periodic behavior, and that's where we're going to use sine and cosine in modeling in sections down the road. But this is kind of a little bit of a precursor to that, and you'll notice here there is a very specific relationship between pi over 4 and 9 pi over 4. The difference is that the 9 pi over 4 has undergone one complete revolution. So, from this we can note that the sine of angle t plus 2 times k times pi, where k is an element of the integers. For any integer value k, sine of t is equivalent to the sine of t plus 2k pi. And the 2 pi part here, the 2 pi is the period. You think about that being a full revolution of my circle. So if I went 4 pi, that just means that I'm doing 1 circle, 2 circles, and then another pi over 4. Okay, that would be that t value. So sine of 17 pi over 4 would also have the equivalent value. With cosine, same behavior exists for the same reasons. We could say that the cosine of t is the same as the cosine of t plus 2k pi, or k an element of the integers, for similar reasons. And that concludes section 7.3.